Okay. Anand, am I audible?
Yeah, you are.
Okay. So we'll start the session. Good afternoon, everybody, and welcome back for the third session of the fourth day of this faculty development program on machine learning and deep learning applications in engineering science. For these sessions, we have resource person Anand Mishra sir. Friends, Anand Mishra having wide experience in the quality assurance, and he has a lead engineering also for the data science project around 6 years. I welcome Anand sir on behalf of Department of Civil Engineering, Government College of Engineering, Karad for this faculty development program. Now I request Anand sir, please proceed the session. Anand sir.
Thank you so much, sir, for your kind introduction about me. And hi, everyone. I am Anand Mishra, and I've been very much fortunate today to join this session to provide my level of experience and knowledge, whatever I have. So the today's topic is all about image captioning. Though you might be familiar about this word image captioning, but let me give you a brief idea about what exactly it is. So under machine learning pattern, there is another concept called deep learning, which is quite advanced machine learning paradigm. So under deep learning, we have a category called computer vision. Let me share my screen with you guys. So can you please confirm, sir, if you can see my screen?
Yes, sir.
Right. So like I talked about word computer vision, what computer vision is all about. Under deep learning, when you talk about any kind of vision, though it's completely about the machine, we are playing with a computer, we are teaching computer how to behave like a human. So under computer vision, we try to give complete information about our real world to the computer so that it can predict, it can give you the output as we observe in our day-to-day life, like it can behave like a human person. But that's a great milestone to achieve it. It has not been that much advanced to achieve, but yeah, there are a lot more development which has already taken place. So one of the things that comes under computer vision is image segmentation, or you can say image captioning. Like if you are seeing my first screen over here, there is an image, and looking at this image, any person, what you will infer what exactly the image is all about. There are so many things in the image. Like you can see a cat. The cats are playing over here, right? A dog is standing, seeing something. There is a background, green grass, flowers. You can see a stone over here, right? And if you talk about this particular image, there are two cats. They have different colors. They are playing. One of the cats is quite bit up to the next cat. So there are so many things, right? So if you have to describe this image to someone, you will certainly look for some kind of relative context in your sentences that can really form a uh, meaningful things and can provide the other person whom you are talking to, whom you are describing to, so that the person can understand what is the image all about. Similarly, okay, so this is the way human behaves. This is something that human has already got. Human has learned since the childhood, right? So what human has got to understand all these things, how actually human perceives the information, how actually human translate the real thing, whatever he sees with the eyes, and translate the objective meaning of the picture or objective meaning of any of the scenes in descriptive form. Descriptive form means in sentence, so that you can transfer this knowledge to somebody else, right? You can describe it in a layman language. So if you have to describe this particular image, you can say, no, there is no formula for this, right? You can just say in contextual meaning that a white dog is standing, number one. You can also say the dog is seeing something with curiosity, right? A white dog is standing on a green grass field. So these are some kind of relevant sentences that describes the image as you can understand. Similarly, for this image, two cats are playing with each other. One of the cats, the black cat, is quite bit up in the air to the next cat. They are playing on the green grass. So you can have a number of description. You can just go on. You can just describe as much as you can. But the main idea uh, behind describing any of the images is it should be relevant to the next person. It should be relevant to understand, right? So your brain has the power, the biological brain has the power to relate the information, whatever you see, and speak about in a relevant manner, right? So image captioning is something like that. It mimics the activity of a human brain, right? So we use some technologies like you have already gone through a few of the introductory concepts about machine learning, artificial intelligence, and yesterday you had a good session with Neeraj who little bit talked about few of the concepts of deep learning. So image captioning falls under deep learning in one of the categories called computer vision. So let's move ahead. This information is a wide range of information, I would say. Like everything starts with artificial intelligence, right? We heard a lot more about artificial intelligence, what it is, and everywhere around the world, this is the big buzz right now. So artificial intelligence, then another box says about machine learning, then comes to computer vision. That means computer vision has the flavor of artificial intelligence plus machine learning. Without machine learning in base, there won't be any kind of artificial intelligence. The possibility will be none, right? So machine learning makes the artificial intelligence and computer vision more powerful to to achieve the things that you want to achieve throughout your experiment or throughout your requirement. So further, to understand a computer vision a bit in detail, here I have classified few of the things that you can understand what computer vision and its applications are. So the first thing that that is object classification, and later object identification, verification, object detection, object landmark detection, object segmentation, and object recognition. These are related with the object. What is object, by the way, over here? This is nothing but the things that you see in your image, in your picture, right? Like in the first slide that you saw two cats and a dog, they will be treated as an object. So machine tries to classify those things in different categories, right? So the object classification, it deals with the broad category of object, whether it is in the photograph or not, whether the cat is present in the photograph or not. The object identification says whether the given object is in this photograph or not. These terms are a bit slightly, overlapping each other. But if you read out between the lines, you will come to understand these are a bit different from each other, right? So object verification is the object in the photograph, whether it's present or not. Again, it talks about the first point, but there is a slight difference. We'll cover this in later on. Object detection, where are the objects in the photograph? It talks about the direction. It talks about some particular location. The landmark detection is what are the key points for the object in the photograph, like whether what kind of color the grass has got, what is the color of the object that you are trying to identify. So one of the peculiar color that you are going to pick, that comes under the landmark detection. Similarly, with the segmentation, what pixels belong to the object in the image. The segmentation part is bit, you can say, it's a kind of mathematical calculation, though everything is quite mathematical calculation behind the scene. But segmentation in particular, it deals with the pixel of the images. Same goes with the object recognition, what objects are in this photograph and where are they. It talks in detail about when you try to implement object recognition. One of the examples you can have is about the facial recognition. Nowadays, almost all of the mobiles, the latest mobiles, Android, be it Android or iOS, that comes with the, the facial locks. What is that thing? That's nothing but a part of computer vision, right? It detects your face, it reads your face, and to read your face, what it does, it actually first it asks you to identify yourself. So that it can learn the pattern of your facial expressions, and expression is nothing but a value of the pixel, right? So it converts it in some mathematical format inside and translate that in real picture. So whenever you come next time to unlock your screen with your facial expression, right, it helps you to unlock the screen. Moving on, here we can understand that where actually we are using the image captioning and where it can really help in the real world. So one of the best examples is self-driving cars, right? In self-driving cars, what happens is it's a driverless car, right? So it runs on a very, very heavy calculation with the help of algorithm. What algorithm does, it captures it trains itself on most of the pattern that you feed inside the algorithm, like roads, the image of the road, and all the rules and regulations that you see on the road, like red light and everything around you, right? It detects it learns the pattern on that. Not only the images, but there is a pattern of how the things will process with the self-driving car, because human drives the car, like it steers the wheel, right? It changes the gear. There are so many things. So, but the computer vision is one of the part which enables self-driving cars to function automatically, right? The second thing, which is a great area of exploration as well, give vision to the visually impaired person. Why I have written over here, because this is one of the good things, and I think would be beneficial if something is really implemented like this in our real life. Like we have a Google map. Earlier it was not there, right? Now we are used to it, and without that we cannot even go in unknown location. It's very easy to navigate. Like the same thing with this vision part, right? When you have this such kind of system, it will help the visually impaired person to navigate around the world, around the street quite easy. And today I will also demonstrate one of the examples that I created, and I had a project kind of thing. So to support this visually impaired person part. The third thing, real-time captions generating through CCTV cameras feed, right? It can also not only the image but the video, and the video is nothing but a sequential images, right? There are 24 frames, I believe, 24 frames per second. When you pass this before your eyes, you feel it as a video, right? But video is nothing but a collection of images in a certain time frame, right? So that can also be captioned, and that can also help in determining lot more things. Suppose if you want to, if there is a criminal moving around the parking in the basement and try to steal the car, if there is a camera feed over there enabled with such a great algorithm capacity, it can detect that person is trying to steal the car, and it can alarm the owner of the car that something malicious is going to happen. So this way, the real-time feed can be also processed with the image captioning part. Right, in healthcare as well, looking at the images of a patient, if computer can describe the disease and diagnosis. Suppose if you have an X-ray, right? If you fit that X-ray, the system, and system can generate, system can let you know, looking at the picture, that this particular area seems to be right with a disease, and there is a diagnosis for this. It can be one of the great applications in the healthcare industry. It can completely change the things. So there are some experiments going on. I recently came to know about a few of the things. I will see if I can show you that as well. And okay, so these were the basic ideas, where what is image captioning, what is computer vision, and what are the applications where this image captioning can really leverage you to help you out in your daily life, right? But image captioning is not that easy. It takes a lot more, time. It takes a lot more training time in terms of algorithm to be trained, to generate and to give you the real output on that. So there are certain processes, like to develop any of the ML model, machine learning model. You have to follow few of the processes. The first thing is the data, right? Data is the core concept behind data science, artificial intelligence, or whatever you name in machine learning context, right? So data in image capturing part, that would be nothing but an image, right? Image collection is the first point, or you can say the data collection is the first point before you go ahead to deal with the image capturing part. So further slides, I have just listed out few of the processes that will take you forward to implement this in general, right? The first thing is data collection. So data collection is a part where you have to deal with, you have to give a lot more time, because data collection is not easy. So in case of images, in terms of deep learning, you cannot do it with one or two images. You have to have at least million of images to process, because deep learning algorithm demands you to feed a lot more data. It's a bit different than the machine learning pattern, right? It demands you to have a lot more data so that it can give you great accuracy and great output. So in terms of collecting the data for related with the image, either you can go with the self-collection. You can just keep on clicking a lot more photographs, but again, this is a very tedious task to collect so many images with the surroundings. It depends on what kind of domain you are going to work for, right? For healthcare, if you take in as an example, you will have to feed the X-ray files, so many reports, right, to the system, and that you cannot click X-ray files every time and then, right? So not to be worried, because the internet is quite helpful, and there are so many communities which are offering free data, right? So that you can use them and you can really train them in your real environment, and you can have the great output. right? So we'll talk about that later. Again, once data is collected, now you have to understand the data. Like I just said about the domain, suppose if you are talking about healthcare domain, so there must be data which denotes, there must be some information which denotes about the particular industry of healthcare, right? You cannot have some data like you can say the road images, the traffic images, the person traveling inside the park to help you with the domain in healthcare. You must have the data related with the only with the healthcare domain, right? Now, once you have data collected, you have got the understanding of data. The third part comes the data cleaning. You cannot have all the mix and match of the data to perform this task. You have to deal with the data cleaning part. When I say data cleaning, that means that a particular functionality that you want to achieve out of your data, like in healthcare, again, if I say chest X-ray, right? So chest X-ray is a particular domain that you want to achieve, and you want to predict based on the images of chest X-ray. You want to train your algorithm, but again, you cannot provide uh, like your broken hand images to achieve the chest X-ray functionality, right? So you have to clean the data. You might be having a lot more data achieved from the data collection pattern related with the healthcare. But in particular, if you want to go for only chest data, you have to clean that data. You have to collect only those data which denotes the chest X-ray, for example, right? So these 3 points: data collection, understanding the data, data cleaning. In any kind of ML model, you have to deal with these things in prior before you go to train your model. The next thing is loading the training set. Once you have the clean data, once you are done with the data, we have processed the data, right? You will go ahead and you will further load those data in a training set, right? And for that, you have to pre-process few of the things, right? Data processing, images, and data processing captions. I will talk about captions in a bit while. Let's talk about images. Like I discussed about data cleaning pattern, in data pre-processing, you have to create such data which your algorithm can really understand. Every algorithm has a pattern, right? So that pattern, one should know how that pattern actually behaves when you apply that particular model, right? So for that requirement, you have to create your data set, right? And you have to feed that data set in the model. For example, over here, images. Suppose it's a algorithm demands only grayscale images. So you cannot have the RGB, the colorful images, right? The grayscale images will have only two colors, black and white. It's a 0 or 1, right? So for that requirement, you have to be sure that your image data is only grayscale data, so that you can go ahead and feed it into the system. The further is data processing about captions. When I say captions is nothing but your descriptive language, the language I am speaking right now, the language you would normally talk with, right? So out of the images, we are trying to extract the meaningful textual information, right? So in image captioning, we have to process two kinds of data. The first thing is the image, and the second thing is the caption. We'll see how captions plays an important role, how we do that in later slides, right? Then pertaining to this image captioning pattern, data preparation using generator function, then we have to embed the word, and then finally we go for the model architecture. We have to decide which model will be suitable and for our requirement. Then we go for inference, and then we evaluate our model. So this is nothing but this is a similar pattern that you can refer in doing any kind of ML practices. So like I said that the internet has got a lot more communities which who offers you a ready-made data, right? So there are two things that I would like to discuss over here. these are the open source. If you say this Flickr 8K or Flickr 30K and Coco, right? Coco stands for Common Objects and Context. These data sets are really rich in terms of its availability, plus in terms of quantity, containing 100K images. This Coco data set has of enormous domain images. You can have a lot more. You just think about the domain, you have the data over there, right? But out of those, what actually you need, you have to get those particular images from there, right? So we have solved almost the problems of data. That is the main core concept behind this image captioning. So Flickr 8K is 8,000 images, 30K is 30,000 images, right? And 180K is quite a huge amount of images. So Coco is one of the best over Flickr, I would say. You can have a lot more examples in real time, right? So let's move ahead. I talked about captions in particular earlier. So it says the captioning is all about merging the two to combine their most powerful attributes. That is CNN and RNN. I am just assuming that you heard the word CNN. It's convolutional neural network, right? And RNN is nothing but recurrent neural network. It's a kind of CNN, the advanced CNN, but it has a bit different logic, which CNN does not have. I will talk about this in detail as well. So how the caption generates, actually looking at the images. The first thing that I talked about is object detection. So you have to identify the object, like in the cat and dog images. You have to identify the cat, the dog, and the grass and the flower, so that you can have a real-time contextual meaningful statement, right? So what CNN does, CNN identifies, we use both the things to achieve the goal of image capturing part, CNN plus RNN. We merge both the output together to produce the meaningful statement, right? So what CNN rules is, CNN just identify your objects in the images, like it will identify the cat, it will identify dog, grass, right? It will give you such kind of output. Once you have this output, we feed this output in RNN, right? RNN, recurrent neural network, behaves in a different way. The RNN was created for the sequential data processing. When it says sequential data, that means collection of images, right? Collection of numerical patterns data, like whatever we are talking is a sequential format, right? We are making some sense when we are speaking, talking to each other. So these kind of sequential data, the RNN is quite capable to perform the operation on, right? So to achieve the goal, we have to feed the data in RNN as well. But what kind of data you will be feeding to RNN? This is the question, right? CNN just dealt with the image data. The RNN will have a textual data to give you the meaningful information, right? We'll see further. This is a pictorial format of displaying how the model actually behaves in within the system. For example, over here, there is an image, right? Input image, you can see giraffes are there. I fed this in CNN, right? CNN will do some kind of calculation internally. That means that it will extract the feature of fully connected layer, right? You can see this image has a size of 224 by 3, right? It's gonna be fed into CNN. Then the feature vector will be created, right? Then over here, the CNN part is done. Till here, CNN part is done. That means we have got the object identified, right? The giraffes are there. Whatever object the CNN can identify, it will break into the pieces. It will feed to the next system, right? Which will be a linear kind of data. Linear kind of data means the whole information will be converted to a vector space. Vector is a single list, right? So all the information will be converted to a vector list. It will be passed to the linear things, right? Oh, from here, from this particular area, right, the RNN pattern starts. Hope you are understanding this. From image to CNN and the CNN to RNN, right? This particular thing in a separate, we'll see how it actually behaves. But over here, I have written LSTM. LSTM as a kind of RNN algorithm, right? Long-term memory, which actually works well to hold the information. It has a kind of memory which CNN lacks in. CNN does not have memory. It just passes the information to the next layer. But this LSTM, right, in particular, it holds the information which was passed from the input source, right? And then it carries the same information as required to the next level. And the same thing happens till the end, till we have the output, right? So it's not only that LSTM is only behaving like this. You have few of the functions enabled inside, right? Above you can see softmax is applied. So when you feed the data, it goes to LSTM and it then goes to softmax, right? Then the next thing starts once again. It carries the information to the next layer. Then you have this information is again processed to this, right? Over here, the softmax is giving you the output of giraffes. Yeah. The CNN identified the giraffe in this picture, it identified the object, and you got this in second operation over here. In real, it cannot be a second operation, right? It can be a multi-layer operation as well. It's a hidden layer, basically. Nobody knows how it actually works, but this is the pictorial format just to give you the academic view of what is happening inside. So the pattern over here, the object got identified and it converted this CNN input got converted into a textual form over here, and it was able to identify that this is giraffe, the only one word, right, about this particular object. So in pieces, it will go on, it will learn the patterns, it will give you the output later on as well, giraffe standing, and so on, so on, so on, so on, right? So I will explain in detail about LSTM, how this works. Moving on, this is a pattern. This is about RNN, right? Before we understand LSTM in detail, we should a little bit talk about this RNN as well. What RNN does actually, right? RNN is recurrent neural network, right? Why it is called recurrent? Because it has got a looping, right? It works in loop. Unlike CNN does not have a loop. Once it is processed, it is processed forever, right? But it has got the loop, right? For example, this A over here, this denotes this neural network pattern, right, of RNN. XT is the input. When you provide the input, it goes through some of the algorithmic calculation, right? And it produces the output. But to produce the output, it has got loop inside. This loop enables this particular neuron activity to remember what was the input inside. It holds for some time, right? And further, it has been broken into multiple patterns. This is a kind of chain. You can add a lot more RNN together. This is a single example of RNN pattern. Now here it is displaying the entire chain of RNN, right? Depends on your input size, depends on your calculation requirement. It can go on, it can produce a lot more different output, right? But this is just RNN. I'm not talking about LSTM right now, right? Now, let's dig inside a little bit about how RNN actually behaves inside, what happens. So when you provide an input inside any neural network in RNN, right, you have the output over here. But further, to maintain the chain and to produce the relevant output in contextual format, right, it has got TANH function. TANH function, probably you can explore it on a website there would be a lot more materials available to understand. In short, it gives you the sigmoid value. What sigmoid does is it produces zero, the output between 0 and 1. So it restricts the output probability between 0 and 1. 0 means the information should not be retained, and when the output is 1, the information should be retained. This is the concept of the single layer RNN. And further, it has been enhanced to LSTM pattern as well. So LSTM in particular is nothing but a multi-layer RNN concept, right? This tan-H function is a kind of sigmoid which gives you the value between 0 and 1, right? I just made it clear once again so that in LSTM you can correlate it with what sigmoid actually does, right? It gives you the ability to sharpen the edges. If you draw a linear line, right? The line, if suppose this is a line like zigzag in case, right? The sigmoid will just smoothen the curve to give you the probability between 0 and 1, right? And further, it will feed the same output to the next level of layer, and it will go on. Further, to understand in detail, like from the previous slide, from here, it was just a single RNN pattern in a loop, right? Over here, it's a single layer RNN, but it's maintaining a chain of output to the further layer, right? And moving on, this particular image is demonstrating about the LSTM pattern, right? But when we talk about LSTM has got a lot more, different concepts of gates. Like in electronic chip, we have a lot more gates, NOR gate, JOR gate, whatever gates you say. I'm not from electronic background, sorry for that. But anyways, the gate concept is also implemented over here as well, right? And this gates enables this LSTM long short-term memory pattern to memorize the things, to forget the things, to keep the things in flow, right? So there are 4 things with this: a cell, an input gate, an output gate, and a forget gate, right? And these 4 things behaves differently, but in a correlation with each other. It helps the next level of gates to, it's a kind of cooperation between 4 guys, right, to achieve the particular things. Let's go a bit in detail. Over here, you can see this arrow has got a meaning. This particular pipeline has got a meaning over here, right? You can see tan-H over here. I'm just trying to make this visualization bit okay for everyone to understand, right? The output is denoted. Sorry, the output is denoted over here. This xt is the input layer, right? What it is actually doing is, I have also mentioned over here what actually these pattern means. The yellow square, it says that this is a neural network layer, right? So the input goes through the neural network over here. There is some process happening. This particular cross within a pink color, it's a point-wise operation, right? It's a kind of calculation, I would say. It multiplies the input with value of 0 and 1. 0, if it is multiplied by 0, the value will not be retained in the system, in the flow, and it will be talking then to the forget gate. It will pass the information to the forget gate that this information is not required to be memorized, right? If the value comes to 1, if it is multiplied by 1, it will go to the addition, right? And the flow will be maintained. That means the one value with one information that will be in the flow, it will be maintained always, right? To produce the fruitful output. Now, with this operation, there comes the tan-H that I just discussed in previous slide over here. What actually tan-H does is a sigmoid, right? It smoothens the value between 0 and 1. This is what helping the further things to memorize the things, right? And when the one value comes after the calculation, it goes to the input gate, right? And this is just a cell. This is just a cell which actually doing, what actually it is doing, it is just calculating based on the operation that you are performing over here, right? Multiplication or addition. There are only two operations, multiplication or addition. That's it, right? You can see the meaning of this line over here is a vector transfer. Vector transfer is nothing but a flow. It's maintaining the flow of the information, transferring to the next calculation area, right? And concatenate, whenever you have this joining, the edges joining, you have the concatenate operation. And the copy operation is when you have two edges going together like this, right? The information over here is copied to the next label. It goes like this. So that was about LSTM. Now this is a bit detailed architecture of CNN, convolutional neural network, right? So this is completely a mathematical concept, but in short over here, I just wanted to show you this particular thing. This is the image, right? And there are so many layers inside. The CNN is nothing but a multi-layer neural operation, right? It's a convolutional, so it has got multi-layer. So when you process the image throughout this operation, the whole pipeline, at the end, what you get? At the end, you have a vector, right? And vector just has a single list. It holds the biases and weights. For biases and weights, I won't be going in detail because that will distract me from this particular image captioning topic. So you can read that bias and weight. That's a very simple concept. So over here, you can see this box denotes the convolutional plus ReLU. ReLU is an activation function. Yesterday, I heard Neeraj was talking about this ReLU. In case if you don't know this is an activation function like tanh. Tanh was sigmoid, right? ReLU also smoothen the curve between 0 and 1. It gives you the probability between 0 and 1, right? And this is one of the activation functions which is widely used, right? And again, there is the pooling layer, fully connected layer, and softmax, right? Max pooling is a concept. Then probably if I will have time after this topic, in case I will go and I will discuss about this as well, right? But this is just a demographic information, so demonstrating information about how the layers are connected with each other. This was the size of the images, right? Then once it is processed with the convolutional pattern, it reduces the size 112, 128, then further again it reduces, then so on. Once you have 1 into 1, right? And from here you can see this is called the fully connected layer. Now here from here you will have the output, right? And the output will be produced again. It will be a vector, right? You need to decode that thing because everything is encoded within this. The LSTM pattern also works with the decoder and encoder patterns. Okay, so far I just discussed almost about the technical aspect, what is happening inside the system, what happens, and what LSTM does, right? Just to rephrase the things, we have to use RNN plus CNN. We have to merge both the things together to produce the image captioning thing output, right? RNN is supposed to give you the textual information, and CNN will identify the object, right? I will quickly give you an idea of one of the projects that I did a few months ago. Just give me a second. Okay. Look at this image. I will show you the code as well, how everything is bundled together to produce this output. But this is one of the examples that will help you to understand what image capturing does actually, right? So just look at this image right now. It's a metro, the gate, the passengers, you can see over here, right? It's a metro station. There are so many things that you can infer out of this in contextual meaning, right? Let me show you quickly what happened. this particular thing. The system, I provided the system a caption about this image, such images, not exactly this image. It was a metro train is waiting with its door opening inside the station as passengers are sitting inside, right? This was the caption, that was the real caption, that which should match with the expected that we are trying to predict through the algorithm, through the machine, right? What actually machine did was it predicted the caption and to see the caption, how realistic this is, just like a human can describe things in using the brain, right? It says a train is parked at a station with doors open to no further passengers. It was an amazing output, right? The real caption was this: a metro train is waiting with its door opening, but the machine also predicted the next caption, which says a train is parked at a station with doors open to no further passengers, right? And this is just a broken pieces of all the calculation, right? It identified the object and it correlated in a sentence using the RNN logic, right? And you can see with each images there is a sentence embedded, right? There's a word, sorry, there's a word embedded, like with a, this one has got train, this one is parked at something, so on, and it completes the whole sentence together. It also counted this end. I don't know why, but this was one of the output as well. So this is what happens when you have image captioning, project. When you apply image captioning project, this is something that you can achieve, right? So my motto was with this project was I wanted to deploy this in a real time on a mobile devices, which is under development right now. This project, till we calculated this project, we covered the most of the things, the prediction part, and it can convert the prediction into textual format, right? And further, it can also let you know to just input any of the images. It will try to give you the idea. It will try to give you the exact output that human can also read and can understand, right? Let's go back to the slide. And this implementation is nothing all about the project that I wanted to talk over here. So the actual problem with this project was, the problem statement was, I wanted to make this project for those people who are visually impaired. I wanted to create a navigation system. With the help of mobile, the person who is visually impaired can navigate the street. Just open your camera and in your mobile device, right? Face the camera. It's not only mobile device. You can have a additional camera as well, right? Like button kind of camera, tuck in your shirt or somewhere, so that, and there would be some, the visual image processing inside with the help of computer, or with the help of some cloud calculation, right? And there would be a earphone plug to the person so that it can listen. The person can listen as well. So the real I can say real image processing was there. That was the purpose to for this project, right? So that's what I have written over here. The underlying analysis aims to aid visually impaired population by navigating and making street crossing a less difficult task for them, right? And further, to the step that I took was the thing that I discussed earlier, data selection, right? The sourcing the data. I use Coco data as well, and Coco data plus my data as well. I collected almost 1,000 data set and try to calculate the things together with the Coco data set, right? So sourcing the data, the labeled images. The best part with Coco data or Flickr data is that the images are all already labeled. When I say it's already labeled, it means you have the captions already there with each and every images, right? You don't have to manually enter the captions. You have the captions already generated for those things, right? But if you are going to work on your own data set, right, you have to create a caption for those images as well. You have to write a descriptive caption in multiple lines. That's again a tedious work. That's why people prefer to download the data and work on that, right? For 500 images, I had to write multiple captions so that I can feed those things in system and can have a realistic, the idea how the system is behaving with my data, right? But in my project, though it was related with the street navigation, so I had to restrict myself to filter out only those data which are really important for me. In Coco dataset, if you go, they have mentioned, they have a categorical data. If you go to search for road, they will just give you road, right? If you go to search for traffic light, there will be traffic light. But again, traffic light cannot stand in the air, right? That will be parked on the road. So such things are something that you have to deal in cleaning your data. That was a tedious work again, because my domain was fixed, just a street navigation with the help of any of the camera, right? So I wanted to have subject like roads, cars, human beings, traffic signals, automobiles. So these are few of the object that I identified for my project, and I just processed with this, right? Further, there was a challenge, the challenge that I just talked about, right? To download the categorical data, because when you download the data for, let's say for transport, it will have a lot more things. The road, the traffic light, that can be irrelevant for your project as well. So you have to filter out. For this purpose, I had to write a small a small Java code to download the images as per my requirement. So this is just one of the snippet, right? We selected the images as per the as per the requirement that we had, but 118K images, right? It's a huge area. Now, to perform the calculation on a deep learning thing, you have to have a very great computational power, right? And for sure, the CPU, the laptop, like people use in normal day, that cannot be used. You should have, the GPU. GPU is more capable than CPUs, because the deep learning calculation is quite heavy. The computational capacity is required, the RAM is required, the hard drive is required. 118K image is not a small piece of things that you can keep in any of the drive and you can access it, right? You have to have a great storage as well. So this is also, again, a great challenge. To perform any of the deep learning tasks, you have to have such facilities, such infrastructure with you, right? So further, what I did as per my project, right? Okay, this is just talking about that the Coco data set has the Western influence, but I wanted to implement this for the Indian context. So I added few of the data that I just talked about, that I had clicked few of the photographs, 500 around, and created the captions on my own, right? Further, like I discussed about RNN and CNN, why they are important. So this is the pre-processing step that I had to follow, right? The pre-processing requires the image and text, image data pre-processing and text data pre-processing. So data size selection is also very much required thing, because it was one of the demo project that I was doing. So I never wanted to go for 118K images. So what I did, just to make it capable, I selected 5040 images, 5,000 from the Coco dataset and 40 images from self-created dataset, right? So that I can save on calculation time, storage time, and there are so many things. Now the further thing is data cleaning. This data cleaning is also, you have two kinds of data, image data and textual data. To clean the data, you need to have both the data cleaned, right? So this is about the textual data. Textual data, there could be a lot more textual information which is not required to feed inside the system, right? So you have to make it clear they are useless, like apostrophe S and something like A, some numerical values, some tokens with number, alphanumerics. These are not required to the system to create the output, right? So we have to be very much clear. We have to be very much clear before you go ahead and before we do any kind of things. So this textual information required in clean pattern requires removing punctuation, converting to lower cases, right? Removing hanging, just I just talked about, remove tokens, removing special tokens, any special words, right? So basically what we are doing over here, we are just keeping the meaningful data with us, which can be fed in the system, right? The further thing is creating a vocabulary, right, of all the unique words. Now you have written 10 times the in a particular captions, like you have created 10 different captions and you initialized all the captions with the, right, or the word a or something similar words which is being repeated every time in your next statement, right? So those things are not required because that will give you a bad output, or it will take a lot more calculation time to save on those things, right? You have to be sure that such things don't exist over there. So creating a vocabulary of all unique words present across all the captions, I just considered words which occur at least 2 times, right, in the entire corpus. A corpus is nothing but a collection of your data set, the textual data set, right? So I limited the occurrence of a particular word only 2 times, right? Now, the terms come for pre-processing of the images, right? Like we did for this textual images. This is for the pre-processing of the images, right? So what I did, I used 3 different models. Why I used 3 different models, I will let you know about this as well. So to process the images, there are though multiple image processing models available, but the best that I learned, and I wanted to make sure that these things are okay. Comparatively, I had to select Inception V3 is one of the models, MobileNet and ResNet 50. Inception V3 and ResNet 50, they are very, very great model, right? MobileNet I had to select because I wanted to deploy my model over a mobile devices. That's why I selected this MobileNet, right? And let me tell you, this MobileNet performs really well. It creates a low weight model which can really be deployed on a mobile devices, because mobile devices does not have 40 GB of RAM or something like that, right? Not even 10 GB of RAM, right? So it will give you the output file, a deployable file, just in MBs, which can easily be managed on the mobile platform, right? Inception V3 is also a great image processing model, which is good and suitable for computer deployment, right? ResNet 50 is again is related with the computer deployment. It cannot be deployed on mobile. It's very heavy. Further, right, there are a few patterns that that we call feature engineering for captions, right? So again, when I'm talking about these captions every time, right, I'm talking about the textual information, right? So textual information is, it also falls in the category of NLP, the natural language processing. This is just an NLP, nothing more, right? But in NLP, somewhere I am using the concept of NLP inside, right? Not to talk in particular about NLP, but concept of NLP is being used throughout the system when I'm dealing with the caption thing, right? So there are 2 dictionaries that I used, Word2IX, that ABC says that returns index of the word ABC, and the second one is returns the word whose index is K. K is the number, the position, you can say, right? When you feed the ABC or any of the word, it actually gives you the index position, right? And when you feed the number of the index, it gives you the word, right? And we have to make sure that the calculation of the length parameter, you know, is actually limited and suitable to the system, like for LSTM, so that it can understand what to keep and what to forget, right? And we use the data generator as well, because we cannot have a small set of data to feed in the system. Like I said, deep learning use a lot more things, a lot more calculation. It requires a lot more data. So we use the data generator as well over there, right? The further we have used the concept of word embedding. Word embedding is nothing but it's making the relevant concept, associating our word to the object identification. Like in the previous image that where I showed you the giraffe, right? The giraffe was produced because of the word embedding pattern, right? And there are multiple word embedding patterns available, but one of the best that you can use is GLOVE, right? GLOVE vectors for, it is global vectors for word representation, right? It gives you, it takes you input as a as a statement, as a sentence of words, right? And it gives you the vectorized format of those sentences, right? And the best thing is that it is quick and it is already pre-trained. You don't have to tell what is supposed to be done, right? You just use globe vectors, right? And it has the contextual capacity to give you the contextual meaning out of it. Further, till here, we are just processing our data, the image data and the textual data, right? The next thing is deciding the model. So like I talked about LSTM, right? We tried LSTM, but besides LSTM, there is another beautiful model that is called attention, right? Later I realized that LSTM is not performing that well. Let's try this attention. Attention was really great, right? This is the name of the person who actually created hard to pronounce, but I think is Dimitri Badanu, maybe. So attention model was the superior model that really worked in achieving the goal, that the output that you saw in the over here, that was achieved. This output was achieved using the attention model. LSTM was actually failing. I do not have that output right now, and I'm sorry I cannot run this code right now because it's going to take longer time. So that would be a bit impossible for me to run the code. But I will quickly go over it. Right. Let's see further. So once the model was built using the attention pattern, right, we have a beautiful output that I just showed you earlier in the code line, right? This was the real prediction that we got the model prediction with this statement, which was quite realistic. You cannot say that this is something given by a machine, not by a human brain, right? A train is parked at a station with doors open to no further passengers. The machine assumed that this train is not going anywhere. I don't know. Maybe it did not see the signal anywhere. It did not see the doors are closed, or something. Something happened inside the thought of the machine, right? So I just tried to give you this idea: real versus prediction. Real was this, and the prediction was this. Further with all the models that I listed over here in this Inception, MobileNet, ResNet. Okay, before we go in detail about what was the conclusion over here, let me give you the idea. When we process the data, the images with this Inception or MobileNet or ResNet, right? The output of these models will be used in attention model, because this is giving you the processed output, right? And how can we use that output in our attention model, in the final model? It gives you the way, it gives you the output file in a that is called pickle file, right? So all the models can produce the pickle file. Pickle file is a really deployable file, right? When you have to deploy the model in a real environment, you create the pickle file, and pickle file just holds the biases, and the weights in output format, right? So Inception produced the pickle, MobileNet produced the pickle, ResNet produced the pickle. Finally, what I did, I just embedded all the pickle. I called all the pickle file using this code, right? And okay, there are so many calculations. I will talk about this, right? And achieve that thing. But to process the Inception or MobileNet or ResNet or process the image using these three, we have to go through, you know, a lot more coding lines to create the pickle file. I'll show you a bit. Further, the conclusion that I am trying to make it over here, right? It's a comparison between these things, right? It says the Inception V3 model. See, the file size is 9 MB and 40 MB, right? The pickle size is 40 MB, right? And the time it took to train the system is 40.54, right? And this is the validation time, 9.72. The MobileNet, comparatively, the file size is 5 MB and 20 MB. Why there are two file sizes? So one is for training set, another one is for validation set, right? So you can see the 31.20 is the time, 10.21 is the time, right? And the ResNet 50 was bit, it is stored on the second position, 33 and 7. Though the file size you can see over here, 9 MB and 40 MB, right? Further, this talks about time taken in seconds to run one epoch. The iteration, the epoch is nothing but the iteration that goes throughout all the neural calculation, right? So for Inception V3, it was 191 seconds for one epoch. For MobileNet, it was 124, and the time for ResNet 50 was 300 seconds. So overall, the performance of this MobileNet, you can see in the previous slide as well in terms of training time and, you know, time in validation. And this is the per epoch time. It is standing out. It is performing out well, right? And in terms of training and validation loss, you can see this MobileNet, the data over here, it says 2.54, 3.93. Rest of them are a bit on higher side, right? Training loss in Inception V3 is a bit lower, but again, looking at the accuracy of time and lot more other factors, this particular model, the Inception, the MobileNet stands out clearly, right? So this was all on the PPT that I had, and thank you so much for giving me this opportunity to discuss about all these things. Let me quickly give you the idea about the code that I went through. Right. Okay. This is the code. The environment for my code is Google Collaboratory, right? It's a free open source for now. Not sure when Google can make it chargeable. So you can just go to, you can just search collab, right, in Google, and you will have this collab notebook open. And this is the Python code. It's a Jupyter kind of notebook that you can see over here. And this is really wonderful because of two reasons. It gives you the way to select the GPU, right? I won't be doing that because that's a chargeable account for me. That's going to charge me. But from here, once you connect it, you can select the GPU and RAM size. You can define everything. It's a virtual machine that it will give you, right? And I don't think this is available except this collab things. Yeah, Microsoft Azure is there, but that's a different concept altogether. To write the code like this, right, you can use this collab. This is really wonderful. So this is where I am just importing all the important libraries to perform the things, right? Further, I have kept everything on a Google Drive, and I have mounted the drive to access my files, all the images files, right? And I just called everything, right? I'm just trying whether the captions against the image is correct or not. Can you see this image file name 064, 064, 64, 64, 64, right? 5 times. And for single file name, I have over here almost 5 captions, right? So whatever object was there, it got identified over here, right? Further, I'm just trying to see what are those things right now, right? And description about, once again, I am just trying to verify after processing whether I have lost any of the information or not, but this is similar to whatever I had earlier before processing, right? And all right, this has also called, over here, I have also called this Inception V3 model, right? And Inception V3 model, because we are using the pre-processed data from Inception V3 as well. So we have called a particular in a hidden layer over here, and it supports the ImageNet weight and bias. It calls the ImageNet weights and bias. ImageNet is a pre-trained model for image processing, and Inception V3 supports that particular thing. And then I converted the things in a vector space, but this resized, right? And here I am deciding the maximum length, how long the caption can be, right? You have to be careful about that because you cannot keep on generating a kind of statement without any full stop, right? That is a bit problem for the real model, whether it's LSTM or attention, right? But attention actually keeps long memory in itself, so it holds a lot more data. It can keep lot more memories, right? Then further, the main thing that I want to talk about, about I am providing, I am processing the data, all the data in a batch size, right? 64, and this is the embedding dimension 256, right? And the vocabulary size I'm defining over here. Further, this is the attention model that I am gonna call with the help of the functions, right? This is all the calculation that you have to define. This is basically the parameter things that you are gonna define, and further, right? You got to encode the input things, and once the process are complete, then you have the decoder patterns, because RNN is all about encoding and decoding. You process the image in coded format, then you have to decode it as an output, right?
Anand sir? Anand sir, am I audible?
Yes, sir.
Sir, it's 3:10.
Oh, I'm so sorry. I did not realize about the time. Okay.
No problem. It's fine. We'll cover few questions. That would be better.
Just give me 2 or 3 more minutes. Let me complete this particular thing. I will.
Sure,
Yeah?
sir.
So, thank you. Okay, so okay. Finally, once things are done, things are processed. I am defining the epoch size 75 for just for testing over here. It can be 100. It depends on your computational capacity, but just to limit my testing perspective, I had keep it a little bit low, and further it's gonna give me the loss, the validation loss and training loss, right? And time taken per second, right, with each iteration. So this is just to give you the idea how the system is actually bundled together. Now I have the loss plot. I can see the loss, how it went up, how it went down, right? And yeah, once you have the things in your place, you just run the model, you train the system, you provide the validation test data, right, like this, and this is the output. I'm sure that this is not easy to go through like this in a code pattern, right? One has to go line by line, but again, there's a limitation of time, and it was kind of introductory session, I just kept it simple and wanted to add this flavor that so that you can see what actually happens in the backend, right? So I think I am done over here, and yep, I'm done. Okay, sir. Let me see the questions.
Yeah, now this session is open for the discussion. Participants can put the query in chat box for an answer.
All right. Okay, the question that I am reading from Sumit Khatri is, what does feature vector dimensions refer to? So feature vector is when you talk about the dimension, right? When you talk about the vector is a kind of list, right? So it has always a one-day list, right? So whatever feature which got extracted from the previous layer, right? That comes to the vector in a one-day dimension. And Vikas Dubey is asking, please tell us what are the libraries are used for this code. Okay, Vikas, there are multiple libraries, but image captioning is, see, it depends what kind of requirement you have. For this particular requirement, right, uh, TensorFlow is one of it. Without TensorFlow, you won't be able to perform deep learning calculation, right? TensorFlow with Keras. So if you go to Colab collaboratory notepad, like I just showed you, right? You can import, it's already there. You can just import TensorFlow STF, and you have the help document over there as well. So obviously the NumPy is one of the things. Scikit-learn is there, right, to perform the calculation, the numerical calculation, and gives you the ability to divide the data into train and test pattern. Okay, Kirti, you said that does these models will work for image captioning in Indian language? Yeah, I'm pretty sure it works, but it's not, language is not a barrier for now. I believe the translator is there to just to convert the language in Hindi or in different languages, right? And the site, I'm not sure about this right now, but Google has this facility. Google has this, kind of class already defined that you can import in NLP pattern, natural language processing pattern, and it translates. Depends on the language you want to use. Sumit, how to deal with the overlap features in the image, especially on the topographic maps? I won't be able to answer it right now. Topographic maps, I never dealt with. This is really beyond of my experience. So I will skip this question for now. Sorry, Sumit. Hi, Deepika. I try to elaborate as much as I can in this limited time about the attention model. Arima, I'm not sure. I never worked on that. I know Arima model is there, but LSTM I try to cover with attention. Hope it made you a bit clear. Suggest one tool which is very efficient for object detection from streaming video like CCTV webcam. Oh, I'm not sure about the tool. I'm sorry for that, but I think, hey, probably connect me on LinkedIn. I will ping you my LinkedIn profile over here. Probably I can answer a lot more questions over here. Amar sir, will that be okay? Are you connected? I will just give you this LinkedIn. Let me see if I can paste it. It's not going through. Okay, search me with this name. Probably you will have, correct me with the LinkedIn profile.
Yes. So Anand sir,
yeah.
Yeah, I think we shall conclude. It is a 3:20.
Yes, sir. Probably. I think I completed my presentation.
Yes.
I hope it was
No,
okay
that is a great
for everyone.
presentation, and presentation was very interesting. I
Thank you,
hope
sir.
that participant got some idea, and they will use in the teaching and research. So Anand sir, thank you for sparing your valuable time and give the exposure on the image captioning as it is a current topic for the research. And
Yeah.
thank you to the audience. Conclude this session, and you will join sharply at 4 p.m. for the fourth session. Thank you.
All right, sir. Thank you so much. So shall I disconnect now?
Yes, sir.
All right. Thank you so much.